Lecture 2, Interrupts and System Calls. Now, we have to step back just a little bit to think about computer organization. A typical program like a word processor, Microsoft Word, Notepad, text edit, anything like that, doesn't have to think about the underlying hardware of the computer. The operating system is responsible, however, for being aware of the details and managing those for everyone. We have talked about a program, and we might have an idea, but we need a formal definition of what is a program. And a program, if you have experience writing one, is a sequence of instructions combined with some data. Okay. At some fundamental level, as far as the computer is concerned, it's all ones and zeros, but context is what makes it actually meaningful. But we have instructions, these are commands that we give the computer to do, and then we have some data. These are necessary for the instructions to work on. Okay. Thus, to execute a program, we need at least the following. We need main memory, we need a system bus, and we need a processor. So main memory is a place where instructions and data are stored. There is a system bus, it's how data get to and from the devices in the system, so how data gets from memory to the processor, how it gets from the processor back to memory. And then the processor is the one that actually does all of the work. It is the element of the system that actually executes the instructions. And we have, in the diagram here, an input device, an output device, because of course a computer that has no input and no output is not super useful. But to qualify as a computer, we need the following things. Now, for our purposes, we're really interested only in focusing on the processor because it matters in the context of interrupts, and that's the real goal for what we need to talk about today. So we'll assume that other courses or other resources have given you some idea about memory. If you are taking concurrently with this a digital interfaces course or anything like that, you would have some idea about system bus and how all of that works. But for now, we are interested just in the CPU. Okay, the CPU is the brain of the computer. It does the following thing basically all of the time that it's running: fetch instructions, decode instructions, and execute them. So fetch is get the instruction from memory, and wherever it is stored, we need to go and retrieve it. Decode is understand what we are being asked to do as the CPU. There are many possible instructions, and it does take some work to actually, figure out whether this given sequence of 1 and 0s is a command that says add, or a command that says divide, or a command that says jump. All of those things have to be decoded, and then actually carry them out. Now, carrying them out is, of course, also very complicated. Sometimes, if it's an addition, there are operands that are involved, but at the very least, we could think of the CPU's workflow as fetch, decode, execute. That is, get the next item that's supposed to be done, figure out what we are supposed to do, and then do it. And that will continue until the program is finished. If the program finishes, some of them are obviously intended to run forever. And different steps of this can be done in parallel, and this is pipelining. So while instruction 1 is being executed, we could be at that very same moment already decoding instruction 2 and already fetching instruction 3. And the length and the complexity of this pipeline system is not something we want to examine here, but is itself kind of an interesting subject in terms of processor design. And processors operate on a certain word size. That is the largest unit. So they might be able to do byte operations and 2-byte operations, but the word size defines how many bits the processor is said to have on its marketing and promotional material. So a 32-bit computer has a 32-bit word size. A 64-bit computer has a 64-bit word size, and that's kind of its standard largest unit on which it operates. Now, your looking here at an IBM 686 CPU. This one happens to belong to a friend of mine who decided this ancient device no longer functioning, we could open it up and take a look. And sure enough, it is actually really quite interesting inside the package itself with all the pins and everything. Most of it is just space for the pins and thermal load so it can dissipate heat, but really the actual chip being examined is quite tiny, and you can see it in the center of the image there. And even then, the majority of what you can see when you can see distinct shapes, those are the registers. And registers are temporary storage locations inside the CPU package, meaning that data is sort of close at hand and ready to access. All of the logic for fetch, decode, execute, storing, all of that stuff, that's all incredibly tiny and incredibly complex. Okay, now CPU instructions are specific to the processor, or at least to the processor family. If you have ever written assembly, then you will know there is usually a book or a guide that tells you, hey, this is the list of all of the possible instructions that can run on this CPU. Depending on the type of your CPU, this could be a lot or it could be relatively few. If you have a complex instruction set processor, and the x86 architecture is one of them, there's really a lot of possible commands. If you have a RISC architecture, the reduced instruction set computing CPU, there are comparatively fewer, but it's really still quite a lot. And the thing is that every CPU is going to be different in what commands it accepts and what the assembly instructions look like. But what's interesting to us at the moment is that your instructions are categorized into two kinds. There are some that are available only in supervisor mode, and some that you can run in any mode, either user mode or supervisor mode. Okay, this necessitates an idea about supervisor mode. So supervisor mode is something we will get into a little bit more later, but the idea being that there are some operations which are a little bit dangerous and we want to restrict it so that not every program can invoke those. So an instruction that would, for example, disable interrupts would be only something that's available in supervisor mode, and trying to run it in user mode is an error, and it will be rejected. Now, CPUs do have these storage locations, and these are registers. As we saw in the uncapped CPU, you can actually see some of the registers there without needing a microscope or anything. And registers may store either data or instructions. Now, management of registers is shared responsibility. There are some registers that are managed by the operating system. There are others that are managed by the program. Now, usually you don't have to manually manage what's in what register. The compiler will take your code and do that calculation and make those changes for you. But there are some critical registers that are managed by the operating system that tell us what's going on right now and allow things to actually execute. So we'll examine a couple of the critical registers. Program counter is the first one in the list, and it is telling us where is the next instruction. So if you consider the program that you want to run as a list of steps, first do this, then do the next thing, then do the third thing, and so on all the way down. The program counter is like ticking the boxes next to each of those instructions, saying, yes, I have completed step 5, and the program counter then says the next thing on your list is step 6. And without that, of course, the CPU would not be able to keep track of where it's supposed to go, what it's supposed to do now. There is a status register, and the status register is used for, as an array of bits to keep track of different flags. It indicates error conditions. Was there a division by 0 error, something like that. Instruction register contains the instruction most recently fetched. The stack pointer points to the top of the stack. That's just a convenience thing. The ability to quickly get to the top of the stack and know where it is helpful. And then there are the general purpose registers, and those are the ones where your program can read and write to them, and they're used to store data, store addresses, whatever is necessary for your program to do. And as I say, for the most part, the compiler will be responsible for actually deciding what gets moved into what register and how a register is managed, because it's quite complicated to do manually, even if you would have to do that in assembly. Objection. Okay, interrupts. All right. I'll tell a motivating example as to why interrupts are important and why they are helpful. So let's imagine that the CPU needs some data, but it takes a variable amount of time to get it. If I am a CPU in this analogy and a book is a particular piece of data that's needed, if the data is in the cache, it's as if the book is in a bookshelf in my office. And we'll pretend I'm actually in my office at that time. Okay. Well, getting it is very quick. It's right there, it's right at hand. I might have to stand up to get it, but getting it is very quick, no big deal. If it's in main memory, it is farther away, and in the worst case scenario, it is very far away. That is, it's on a magnetic hard drive. And a magnetic hard drive, in this analogy, is the same as if I have to get the book from Library and Archives Canada, which is, according to Google Maps, 550 kilometers or so away from my office, and I can only get it at walking speed. Okay. The analogy is slightly tortured because the CPU doesn't go get the data, it signals for it, and then it has to wait to arrive. So it's more like I call Library and Archives Canada and I say, hey, I would really like this book, and they say, yes, we'll have it, we'll dispatch somebody to deliver it to you right away. They hand that poor person the book, and that person has to walk 550 kilometers to deliver the book to me. Okay. Now, if I used polling as a strategy for determining when the book has arrived, that would be somewhat inefficient, as you might imagine. How often will I check, and how much time will I spend checking? If the person who's traveling walks at a speed of 5 kilometers an hour or something, this is a really long time. However, better is interrupts. That is, I get a notification when the book that I asked for has arrived. And that's like, I will just stop what I was doing that needed that book, which is not currently available, and I can work on something else in the meantime. And then if somebody knocks on my door, then I can pause what I'm doing, and I can go get the book. Now, pause what I'm doing and get the book are work, and there is a certain order about how to do these correctly and do it well, which we will examine shortly. So in the analogy, I'm the CPU and I was interrupted and I had to deal with that interruption. And the same is true in the computer. So interrupts can come from lots and lots of sources, but we'll classify them as being one of about 4 categories. Number 1, something happens in the program. So there is a division by 0 error in your program, or you try to dereference a null pointer and you get a segmentation fault. The program is the cause of the interrupt, and that is what you get told about. So a bad thing happened, and now you can attempt to deal with it. The second source that things could generate an interrupt is the timer. So a configured timer within the processor expires. This is used to update the system clock. Every second when the second changes, you get an interrupt that says, hey, update the system clock in the corner, and that's a way to do it. Input and output devices will also generate interrupts when an I/O controller signals successful or unsuccessful completion of an operation, such as reading something from disk. And the fourth thing is some sort of hardware failure. So if power goes out, you might actually get sent an interrupt from the UPS, the uninterruptible power supply, that tells your computer, hey, you should know that main power has gone out, which might be a trigger to save work and shut down cleanly in case power is not restored in time. So interrupts are intended to improve processor utilization. This is because CPU time is ultimately fairly valuable. The CPU will be under load quite frequently, and the more efficient use we can get out of it, the better we're doing. So we want to improve this utilization being defined as the fraction of the time that the CPU is doing useful work. So the CPU can issue a read from memory, work on something else, and then be interrupted when data has arrived from memory. Now, when an interrupt takes place, the CPU can choose to ignore it. That's usually fairly rare. Interruptions usually contain some sort of important information, or at least require some sort of response. The video format doesn't make this very easy, but in a normal lecture, if a student puts up their hand and they have a question, it's rude of me to not take that question, even if my answer is let's discuss this after class, because it's not relevant to what we're talking about, or it would take too long to explain. I should handle that in some way. I can ignore it if I really must, and ignoring can be temporary. I might want to finish this slide before I'm willing to take that question, or I might, for time reasons, not be able to handle it right this second. Similarly, if I'm already answering somebody else's question, if another person puts their hand up and wants to ask a question, that's going to wait until I finished handling the first question, just because, that's generally polite. So, yeah, interrupts usually should be handled. And what I'm going to do, if you break down the steps, so I'm talking about whatever's on this slide, surely, truly exciting, I'm droning on about some subject, and if you're lucky enough to have an early morning lecture, you're probably thinking, how could I possibly stay awake during this? But I'm droning on about this topic, and someone puts their hand up, and at that point, if I want to handle it well, what I have to do is pause what I'm doing, and also remember where I left off. And that is saving some state somewhere. Now, okay, professors are not necessarily good at that. There can be a lot of staring at the projector screen and going, what was I talking about again? I simply can't remember. Can someone remind me? And the same is true between lectures. Some people will leave off at the end of a lecture, and then at the beginning of the next one, the professor might ask somebody, does anybody remember where we paused on Friday? That's because professors don't usually write down where they left off. And the CPU does have to do that. The CPU does have to take some notes about what it was doing so it can resume from the same point later. And sometimes professors do that. In one term, when I taught two sections of the same course, one in the morning and one in the afternoon, I would just note down in my notes at the end of each lecture where we had stopped, because it's totally possible that we'd have midterm week, and I come back from midterm week and I go, in this class did we finish lecture 17, or were we on lecture 17 slide 10? I don't know. So writing it down is worth your while. Now, after handling the interrupt, there is a certain amount of work to restore the state, to pick up again where we left off. Now, the operating system really does do all of those steps, and by storing the state, it really does write it down somewhere in memory, deals with the interrupt however is appropriate, and then restores the state of the previous execution. And the CPU can be in the middle of something which should not be interrupted, in which case interrupts can be temporarily disabled, and interrupts can have different priorities. So here's the thing where interrupts and their priorities might matter. If I'm using the professor analogy again, if I say that all questions should be saved until the end of the lecture, that's temporarily disabling interrupts. It's not as nice. You do want to be able to ask your question in a timely manner, but it's not as bad as just totally being ignored. Interrupts do tend to have a priority, so if multiple interrupts are pending, the highest priority one will be dealt with first. To also torture the professor analogy a little bit further, suppose that my lecture, and it's an in-person lecture, is being attended by Her Majesty the Queen. If Her Majesty should have a question, it is very likely I will take her question first. If for no other reason, then she could say off with his head and actually make that happen. So, to avoid that, it is generally not recommended to be decapitated, at least for long-term longevity. Then I would maybe give some priority to that question. No offense, though. Now, if you have multiple interrupts in a short period of time, you can end up with one of the two scenarios here. And the first one that's shown is what happens when interrupts are sequential. So interrupt handler X runs to completion, and then interrupt handler Y happens after that. That's what happens when two people want to ask a question at the same time. I answer one question completely, and then I go on to the next one. But if the second interrupt is higher in priority, it could happen that we might interrupt the interruption. So we are handling the interrupt here X, and there is another interruption here, and we handle interrupt handler Y, and finish with that before resuming where we were in interrupt handler X, which then runs to completion and then returns control to the standard program. You could have either of those situations. Your system could actually have both of those things if you want. A low priority interrupt handler could be suspended to deal with a high priority one. That is okay. System design could support either one of those. So I've talked about storing and restoring state. And the operating system is responsible for storing the program state when an interrupt occurs. It has to be put somewhere. And the state that is interesting here is the state of the CPU, that is, what is it doing, and state is the values of the registers, the program counter, the instruction register, the general purpose registers. If we just take good notes and write all of those things down, then we have everything we need to resume the execution of that when the interrupt is handled. So that's what we do. We usually push them onto the stack or store them in some other designated location. When the interrupt is finished, those values are taken off the stack and put into the registers again. And after that, program execution can continue almost as if the interruption never took place. It won't change the outcome of the program if the program is written correctly, but it could increase the time it takes to actually execute. Okay. Now, it may occur to you that this example where we pause one program, handle the interrupt, and resume that program is maybe not what happens. Because you could have multiple programs, in which case there is the possibility that a different program will be restored instead of the one that was running at the time of the interruption. Yeah, that can happen. We've stored the state of the executing program, and the operating system can pick it up anytime, so it can run something else now instead. This is a matter of scheduling, and it's up to the operating system, and from our view in application programming, it is pretty much out of our control. This is something we're going to talk about quite a lot when we talk about concurrency, which is that the operating system does whatever it wants, and you don't really get to choose that, so you have to write your program such that it is correct no matter what order of execution the operating system chooses for the various programs, and recognizing that it can suspend your program at any time, switch to a different one, and then switch back again at any time. So that's mostly out of our control, and we have to be aware of it, we have to be prepared for it, we might have to deal with it, but we can't choose scheduling. That, again, is the domain of the operating system. Should you take an operating systems course following this, then you will learn all about that, actually, when you take the operating system course, because scheduling is a major component of that. Okay. Now, a lot of the things the operating system does are executed without your manual intervention. You don't have to worry about them. The scheduler runs when it is supposed to. However, there are certain system calls that we want to actually trigger. We want to invoke them. We want to get them. There are interrupts that are generated by hardware, the keyboard signals that you pressed F1. There's interrupts generated by software as well, and that's how we actually specifically invoke a system call. In the words of Admiral Ackbar, it's a trap. Okay, trap is the term for a software-generated exception. And it can be generated by an error, an invalid instruction, but a user program can deliberately invoke the trap without that being wrong or without it being a problem. Now, a software-generated interrupt could be an error. Now, if that is the case, the operating system has a default way of handling that problem. The usual strategy is sending the exception to the program that caused it. So there was a division by zero error in your program, it generates an interrupt, and that is delivered to the program that is responsible for the division by zero, and that is usually fatal to the offending program. You can sometimes deal with an exception if you use, in, say, C++, Java, C#, anything like that, some sort of try and catch functionality. That's fine. You can handle that exception, and there are some exceptions that you can handle and some that you shouldn't. And the same is true with interrupts from your program. If something goes wrong, it could be handled, but most likely it's not. And if it's unhandled, it terminates the program. So yeah, sometimes it can be handled, other times it just can't be, and the program is just going to die. However, sometimes we intentionally want to use the trap to get the operating system's attention. So I've already introduced the idea previously of user mode versus supervisor mode, or kernel mode as it's sometimes referred to, instructions. And kernel, if we haven't gone over it previously, is the core of the operating system. It is, the center part. It's the most important part. And in supervisor mode, we can do absolutely everything. Any instruction that is supported by the CPU, any operation. And things that are seemingly simple, like reading from disk, writing to console, those are actually requiring privileged instructions. They're common operations, but every time you want to do them, we have to ask the operating system to do it for us. Now, modern processors track what mode they're in using the mode bit. Of course, even more modern processors could have multi-bit variable for this, so it's not just 0 or 1, but a simple version just has 0 or 1, user mode, kernel mode. At boot up, the computer starts in kernel mode as the operating system is started and loaded, but user programs always are started in user mode. And that doesn't matter if you're an administrator on the system, you're still a user, it still runs in user mode, only the operating system runs in kernel mode. And when a trap or interrupt occurs, this wakes up the operating system, which was previously just sleeping, waiting to be told something to do. And the mode bit is set to kernel mode. The operating system does whatever it needs to do, and when it is finished, the system goes back to user mode before the user program resumes. So if you wanted to, in a text editor, send some data to a printer, it looks something like this. There is a user process executing. Well, we're just running the program in the normal way. At some point, we take an action that results in a system call. In this case, we're going to go to the print button, click it. That results in a system call. That generates a trap. This wakes up the operating system. The operating system will activate. Mode bit is set to 0, so kernel mode is activated. It executes whatever it needs to do to run the system call, so prepare the data, send it to the printer, whatever is required. And before we return from the system call, mode bit is set back to 1, that is putting it back in user mode, and then we return, and the user process can continue executing from that point. And yeah, that's what we have to do. Because interacting with the printer, that's a hardware device. It's the job of the operating system, and the user process can't do that on its own. So to print out the data, we can prepare all we want, but we can then say to the operating system, please do this for me. And we trigger that with the trap, and the system responds to actually do what you asked it to do. Okay, so why do we have user and supervisor modes? Well, as Uncle Ben said to Spider-Man, no, wait, I think I got this wrong. What I think he actually said was, with great power comes great responsibility. And many of the reasons for this are the same as why we have just regular user accounts and we have administrator accounts, and it is to protect the system and its integrity against users who are both errant, just making mistakes, as well as users who are malicious. And just to give you an example, a program might want to use an I/O device, and another program wants to use the same one. We'll say we're going to do a read from disk. So program 1 tries to read some data from disk. This takes a certain amount of time. If program 2 wants to read from the same disk, the operating system forces program 2 to wait its turn. Well, without the operating system, it would be responsibility of authors of program 2 to check, can I use the disk now? No, okay, I'll add myself to the queue, wait patiently for the device to become available, and then execute our request. This could work if everybody plays nicely. That kind of thing could happen in a world where it is a NASA space probe and everybody who writes programs on this thing works at NASA, and it's not run by regular users. You don't have multiple users. It just runs these 5 things that NASA has programmed it to do. That might be okay. But for a general purpose operating system, that's not going to work. Without enforcement of rules, then somebody will do something nasty. Program 2 could cancel outstanding requests from other programs to get to jump to the front of the line if there was no enforcement of rules, so we definitely don't want that. That kind of bad behavior is possible and should be avoided. Now, there is a definite performance trade-off for that. Exceptions are expensive, and they're also expensive in like a regular program. If you have a try-catch, it's a reason why exception as control flow, as it's known, is an anti-pattern, that you shouldn't be using exceptions for normal situations, which you should be able to handle. You should use exceptions for exceptional cases. And the thing is that traps are expensive. Switching from user mode to kernel mode takes a fair number of instructions and takes some time. So it would be faster if everything ran in kernel mode and there would be no time switching. However, it is judged that in a general purpose operating system, the decrease in performance is worth it for the increase in security and integrity that this provides. So we'll do an example of reading from disk. And we're going to be looking at a C code version of reading data from a file. We have not yet talked really about files, and that's an upcoming topic, so we shouldn't get too caught up in the details about what is a file descriptor and those sorts of things. But this is an opportunity to introduce kind of the format in which a lot of these things are introduced in the course. So up at the top of the slide, we have a definition for the function. And the return type here is size t. It's a size type. It's just an integer. And then we have a number of parameters, and read takes 3 parameters. The first one is a file descriptor. That is, what file are we talking about? File descriptor is a return value from a previous call to the open system call. We have a buffer, that is a destination where the data is going to be read to. And then we have a count, and count is how many bytes of data we should actually read at the most. So you'll notice in the example, int bytes read, so we're assigning the value here as the return value here from read with this file into this buffer, this many bytes. And the number of bytes successfully read might not be exactly the same as the number that you asked for. Why is that? Well, you might have asked to read 1,000 bytes, but the file in question only contains 200. We'll only read 200 bytes, and we'll be told, yep, we read 200 bytes. That is fine. So, yeah, we should be paying attention to these file definitions to the definitions of system calls, and we should pay attention to how to read them and make sense of them. You should also take a look when the opportunity arises, if you are curious about one of these, at the man pages for those. And for that, there is a website, Man7, where you can get a good description of what is actually going on. It will tell you about the parameters, what they mean, how the system call works, if there are any known bugs with it. That can happen occasionally. And so if you're having trouble and the function isn't doing what you think it should do, one of the first things I'll tell you is you should read the man page associated with this. Man pages in this case being manual pages. Okay. So yeah, the system call documentation is important. Finding and reading this information is actually a key skill, and you will find it, like I said, for a lot of the standard Unix calls at man7.org. You can look at other resources for Linux system calls. If it is a specific code library, later on we're going to introduce the curl library. Well, the curl website gives you a breakdown of how all of those system calls or how all those function calls work, so you should take a look at those because it will really help you with figuring out how to actually use them effectively. Okay, now to actually execute this read system call, well, what happens? The parameters are pushed onto the stack, and that's just how normally a procedure is called in C or C++. And then we go to the read function. And this is a normal instruction to go to another function, but it's the read function that does all the setup and asks the operating system for some help. It puts its identifier in a predefined location. This is typically in a specific register. And then it executes the trap instruction, which activates the operating system. So when the operating system wakes up, there is some work to save the state of the currently executing process. We've switched into kernel mode, and control transfers to the interrupt handler at that point within the kernel. And the handler for the trap examines the request, and it does that by looking at the identifier that was put into the predetermined location. So if read has an identifier of, making up a number entirely, 5, when the trap handler wakes up, it sees the request is of type 5, and then it knows what request handler should execute, the one that corresponds to read from a file. That routine will then execute. It takes however long it takes, and when it's finished, control is returned back to the read call within your program, and then there's a return statement in there, and your program continues executing. So okay, that is an example of a system call. This is a blocking system call, and that means that we wait for the result. When we issue the read instruction, when we issue the read command in our program, we're willing to wait until it's done before we can continue. Because after the read here executes, the next thing that happens is the result is assigned into this variable here, bytes read. And we can't go on until we have that result. So while our program is waiting for the operating system to be done, it can't continue. It is suspended. Okay. Let's imagine a slightly more complex example. And this uses some things that are a little bit Linux specific, but it's a very simple program. It reads a file and prints it out. Hopefully, you've become sort of familiar enough with the concept of C to be comfortable with reading this code along with me. So up at the top of the file, we have some includes of some standard libraries. There's the standard IO library, the standard library, the Unix standard library, the string library, and the last one here is file control, FCNTL. There is a non-zero chance that at some point I will refer to this as function control. That's not correct. It's file control. And just remember that if ever I should say the wrong name. Okay. We have declared a function void read file, which takes a parameter in fd. Implementation will be shown below main. Now, main will check the list of arguments that is provided. If it's the wrong size, that is to say, if it's not 2 arguments, it prints out a usage message to tell you about how you should actually invoke this program. Those kinds of things are nice to users. It makes it a little bit clearer what they have to do. Okay, so our next line after that is int fd is assigned open argv1 read only. In our next topic, we'll talk about what it means to open a file and what does read-only mean and all of that. But just for now, take my word for it that this opens a file, and argv1 is the first argument after the name of the executable. So whatever file name was passed in on the command line, that's the file that we open, and we open it in read-only mode. Most system calls return a value. That value is frequently an integer, and it is wise to check it and see if it is valid. So in FD here, if it's -1, that indicates that open failed for some reason. Maybe it's because you gave in a file name that just doesn't exist. And okay, in that case, we can't go on, so we will exit. We will then call the read file function, which presumably reads the file. We will close the file when we are done, and then we will return at the end of the program. Okay, the implementation of read file looks like this. We declare a buffer size of 256. We then allocate a buffer of that size. And in this loop, while we are reading the file, so it's a while true loop here, we will memset the buffer, so set all of the bytes in it to 0. We will then read the file using the read system call, and we're going to read it from the file descriptor fd into this buffer named buffer, and we read buff size -1. Okay, why -1? The answer is we're going to print it out, and we need a null terminator at the end of our buffer. So if we kept reading all the way to the end, we would fill up the buffer completely, and there would be no null terminator, meaning this printf statement here could actually go wrong. Now read returns to us the number of bytes that was successfully read, and if that is 0, it means we've reached the end of the file. If you try to read from a file and you get no data, that's the end. We've got it all. We're done. So it doesn't matter if the file is not a nice even multiple of 256 bytes. It doesn't matter if the file is empty. It doesn't matter if the file is really large. We're just going to read it a little chunk at a time, and each chunk that we read, we will then print out. And we'll see also that read automatically advances through the file, so we don't have to remember where we were. And so we will print each part of the file, and then we will print at the end of file, and we will remember, as is polite, to deallocate our memory here at the end. Okay, so looking back over this example, what things were system calls? Well, going back to main, open is a system call. Printf actually requires us to ask the operating system for some help because we're printing to the console, so it's not as straightforward as it sounds. Close is a system call as well, and read is a system call, and so is free. So even in this fairly small program, we have a large number of system calls. Not every program will have this density of system calls per line. However, this is a pretty good example of just a simple program that yet somehow asks the operating system to do a lot of its work. Okay, so to recap what happens with a system call, and this happens in that program every time we open, read, printf, free, malloc, any of those things. User program pushes arguments onto the stack. User program invokes a system call. The system call puts its identifier in the designated location. The system call implementation issues that trap instruction. The operating system responds to the interrupt and examines the identifier in the designated location. The operating system runs the system call handler that corresponds to that identifier. And when the handler is finished, control exits the kernel and goes back to the system call. We return to user mode, and then the system call returns control to the user program. So it's a lot of work that the operating system has to do, and even our simple program takes a non-trivial amount of time because of all of the times we have to switch into the operating system and switch back. Now, if the example didn't necessarily make a huge amount of sense to you yet, because we haven't talked about the meanings of open and read and what have you, don't worry. That will be our next topic, which is about files in general and how to work with them in your C code. So we'll pick up again over in that next video.